Thank you very much, Claudia, for this nice introduction. So it's now my turn to show you some activities that I had. So now I'm based actually at Helmholtz Institute Ulm in Germany, but what I'm presenting is related to what I did at Institute for Energy Technology in Norway. It was related on a research project of Research Council of Norway founding. So I promised to give a presentation on combining actually both anodes and borohydride-based electrolytes for solid-state batteries. So I will try to do my best to try to give an overview about both applications. And okay. So first, the motivation is to, in fact, we had worked for means a lot of work about hydrides and their functionality. So one of course, the motivation is to try to broaden the application of hydrides and their functionalities, and mainly in batteries. And one of the motivation also is because this of high demand actually for application in electric cars, so we need high energy density materials. And in the case, as was shown in the, many presentations and also this morning with Professor Ishikawa, that magnesium hydride, for example, can undergo conversion reaction with a high capacity with more than 2,000 milliampere-hour per gram. The other also application of hydrides is application in solid-state electrolyte that I will try also to give a bit some of the work that we did in the past. Of course, there's no doubt that these materials, this application can have a huge impact on in the future because of application in solid-state batteries, which are much more safer. So for the anode part, I will. So this was in collaboration with Professor Ichikawa in Hiroshima University, with other partners from Oslo University. So this is an overview about the different anodes actually that can be used based on hydrides in batteries. If you compare, for example, magnesium hydride to graphite, we could see that there's a huge interest, difference comparing to the volumetric and gravimetric energy capacity. Also, other, of course, hydrides have been calculated, which is not necessarily, based on some theoretical calculation, not necessarily active in electrochemical system. So we focused on magnesium hydride, and here I tried also to make some small comparison with the application in a battery and compare to some anti-alkylation processes. So for example, the most famous electrodes which has undergone an electrochemical process, they have usually quite a rather, and the comparison here is based on two parameters, volume change and capacity, which is usually an important factors for either in solid state or in normal batteries. So if we could see anti-alkylation, usually they have low volume change. However, they have a rather low, which is good. The volume is small. However, usually capacity bit around 200 milliampere per gram. The other process is owing reaction, which is in case, for example, in silicon, we have quite really high capacity. But there's a lot of issues with silicon that hinder its application. In fact, which is the huge, large volume expansion, which is a big problem which leads to polarization of this electrode. So this question is how to conciliate these two. It means how to have low volume change and high capacity. So it seems hydrides can be fit in this direction, which have high capacity and rather low volume change. So we started with some work on trying to see what is the morphology change when we synthesize different material grade from magnesium hydride and see how the morphology and the different properties can change. So we synthesized different materials. I will not go in the details on the different, this was different Born million of the material, different conditions. And this is, from X-ray diffraction, it's not easy to get something, the difference between the materials, but we could see really that from the materials milling under hydrogen reactive ball milling under hydrogen conditions, have rather much more pure materials. So we took these samples and tried to put these cells in the cells, and we got some different behaviors, and we understood that this can be something, I mean, there's an effect on the morphology and quality. And the best sample here, it's, as you can see, is the one which is related to material synthesized under hydrogen conditions. So we wanted to understand why there's a capacitive fad in this material during cycling. So we looked at using transmission electron microscopy, and we could see that before and after cycling for different materials, after 5, 10, and 24-hour bone milling, and before and after cycling, we could see that there's a change in the morphology of the materials. And however, between the different materials, after cycling, they look quite similar. I mean, there's some control. It seems there's some control of the morphology during cycling, whatever the starting material. And then we tried to look at the mechanism. We were not sure, but we thought that there's an issue. There's a problem, in fact, with these materials because it generates lithium hydride and magnesium. And lithium hydride is an insulator, and it seems that something happening with in relation to the electrolyte. And as I say, this is a conversion mechanism. Means that we start with one fresh system, and then we originate new phases. So it means that we originate new phases with the new surfaces. So this maybe has something to do with electrolyte. Also, once we pointed out the issues with electrolyte, we tried to see what happened if we use the same material in a solid state system. And this is what, I mean, this was just a quick experiment to see what happened with the solid electrolyte and liquid electrolyte. And we can see that this is a really interesting change in the reversibility. And in this case, I will come back to this kind of electrolyte we used here, and this experiment was done at room temperature. So we could see that in significant improvement in the reversibility when we use a solid electrolyte. So we also tried to understand, I mean, from just based on some experiment and some literature, and also we could see here that starting from one phase and including some additives and binders, we form two new phases, however, in a larger volume. As I said, this is undergoing at least 80% volume change, so this can regenerate a new volume, and we could see that the final state could be different from the initial state after one full cycle, where the volume is changed after cycling. So it means that there is some change in the volume of the material. But this seems that I mean, the solid electrolyte can help to confine, let's say, the material in limited space that can avoid the issues related to the detachment of lithium hydride. So so then we moved categorically to the solid state systems, and we used in this case a lithium borohydride as electrolyte, and we tried to work with magnesium hydride also with addition with some cobalt oxide, which in fact also conversion type material. This is some data about the interest about solid state batteries. You probably know that there's a lot of car producers that are now promoting the production of solid-state batteries. I think these dates are always shifted. This was 2020 by Toyota, but I think it's again shifted by 3 or 5 years again because of the challenge on working on solid-state batteries. So so I will skip this. I mean, it was clear that the solid-state batteries, there's a lot of interest and regarding increase in the energy density, and also the issues regarding the safety, in fact, which is important in solid-state batteries. So this is the really simple way how to prepare a solid-state system by mixing the solid electrolyte with additive and active material, which is pressed together with the solid-state electrolyte. So first we try to analyze our magnesium hydride without any additive, and we have obtained this nice curves with of the cycling, which is really with the high low polarization and quite good capacity retention. And this was, I mean, without no additive added on it. In fact, but during the 1250 cycles, the capacity is decreasing. And this is another presentation of this cycling. We could see this is really reproducible. And the people working, for example, with lithium iron phosphate, they could recognize that this is something really interesting, that this plateau shape, and it can be reproduced. And this was done, I mean, this is, I mean, it's less than 5 years, let's say, since the discovery from the group of Professor Ishikawa of this work. So this is, I mean, needs to be reinforced, needs more research, of course, to be strengthened in this direction to use these materials as anodes. So, as I said, there was also some capacity factors. We tried to improve the cyclability with the adding by some cobalt oxide, which could have some benefit, because cobalt oxide, it can play a role of catalyst, but also it can provide additional capacity. So the challenge of mixing cobalt oxide with magnesium hydride was related to the ball milling. So we thought that is probably not a good idea, because mixing an oxide with an hydride can lead to the formation of other compounds. And in fact, by ball milling, these two materials for 3 hours is enough to form this magnesium cobalt hydride, which is known in the literature, but it acts a really bad anode in the batteries. So it was not our aim. So our aim was to get an Antimate mixer between these two. In fact, this is possible after just less than an hour of milling. And here in the X-ray diffraction, we could see that these two it's possible to form this Antimate mixing of magnesium hydride and cobalt oxide. So this is the X-ray diffraction patterns, and we can see that we have we could recognize the two plateaus belonging to the cobalt oxide first, and then to the magnesium hydride, and then which is reversible. And the only thing we could notice here, that there's a decrease of this plateau during cycling, without any decrease in the capacity. So it means that cobalt oxide is still remains active, even though the plateau is disappearing. So it seems that there's some, and we know that cobalt oxide is undergoing some formation. It has some dispersive effect in the material, which is also a good conversion type material. So we also did some rate capability, which they look quite interesting, without really a lot of change in the capacity, which is quite stable during 20 cycles. Yes, so we looked at also the interface, and also the XPS confirmed also the reversibility of the in parallel way. I mean, there's no interaction between the cobalt oxide and magnesium hydride. So to summarize this part, so I would say that we succeed to synthesize a hydride oxide-based anode, which is have high capacity, and this had led, in fact, to a nanocomposite material in a reversible yield and low discharge charge hysteresis, and with a mitigated kinetic effect. And this is something we need to forward it and study it in more details. So I'll move now to the next part, which is related to solid-state electrolytes, if I still have some time. And so we start with some materials based on lithium borohydride iodide and lithium sulfide phosphorus sulfide. And the idea comes, in fact, with the fact that this lithium sulfide electrolyte, which is known in literature, has some stability issues. So we tried to mix it with the lithium borohydride system. So we didn't use lithium borohydride, we tried to use this high temperature stabilizer. Why this choice? Because we wanted to have some system which is monotonous, increasing the conductivity, which is rather normal in battery system. No one wants to have this phase transition during using the battery at different temperatures. So we mixed these two systems. The first one is amorphous, and the second one is hexagonal, which is known for the battery community. And we tried to measure the conductivity at room temperature, and we found that there's some increase in the conductivity when you increase the amount of borohydride system. So this was the key point, and we went further and try to understand what is happening. So this is the impedance for the conductivity measurement, and we can see easily that there is a nice shape for the system showing the best conductivity, or the other one showing high conductivity with some different profiles. So there's some isotropy happening, which can lead to high conductivity with low resistance. So we measured the different compositions, and we could see that the conductivity is increasing when we add this amount of lithium borohydride. Then it's again decreasing after when it's rich with a lot of lithium borohydride. So we tried to do the in situ on this and try to see what happened in using in situ, and we could see that we have some change in the X-ray diffraction pattern, and it's undergoing amorphous part with some still presence of lithium borohydride iodide, which is indicated here in thick with the ticks. So so then. It seems that there's something happening around 150, and we went again for our partners. So this work was done with collaboration with Tohoku University. We measured again the conductivity, and we found that mixing these two systems can, at certain ratio, can lead to this quite rather high conductivity, which is suitable for solid-state battery application. We try to understand what we formed in this specific system. We could see here that we have the addition of lithium borohydride. This is a Raman spectroscopy, trying to understand if we really still have the BH4 in the system. So we could easily recognize the lithium phosphorus sulfide. However, for the BH4, it is a decrease of the kind of, the peak becomes less defined, and we have this decrease in the symmetry. But however, this is enough to attribute this stretching and bounding to BH4, the presence of BH4 in the system. So we had some collaboration with calculation modeling. They tried to explain what happens during adding this gradual addition of lithium iodide and phosphorus sulfide, and it seems there's some accommodation in the BH4 distances, which can lead to some increase in the conductivity of lithium. And also the calculation of using barrier height, the activation energy seems quite in a good agreement what we have measured with experimentally. So this is the battery cycling, so it seems very promising for application. This was done at 50 degrees using an electrode of titanium sulfide, and we could see it's quite really reproducible. And regarding the electrochemical windows, we could say that it's really stable at 5 volt. However, some issues at at some small perturbation. So this is a really small current, which is 1/10 of micron. So I think we assume this was related to some contact issues in the system of the cells. The last maybe point is we also instead of iodide we used the chloride. So we tried to study this system. So quickly I will just give a short. We know that with the chloride, in fact, we don't form this hexagonal phase because the phase is reversed back when it's cooled down. So we could recognize here the lithium borohydride and the lithium chloride, and after addition of 1% of phosphorus sulfide, we could see that there's a disappearance of lithium chloride, while we could still see the peaks of lithium borohydride. So this was also studied by measured the conductivity of two systems at different ratios with 10% of phosphorus sulfide and 20% of sulfur sulfide. We see there's a big difference in the conductivity profiles. We could see the first one had undergoes some phase transformation and becomes then stable with quite rather high conductivity. The other one, it stays so low, so we can see, and it's also quite stable. And we measured also the activation energy from the slope, and we got something around 0.4 electron volt. So we also had the in situ, and we could see that there's a amorphization of the system around 60 degrees. However, I would like to mention also these materials were also annealed before the application in batteries. So for example, the B here, it's the annealed sample at 150. As we could see, it's stable until 200. I mean, the application in battery can be, we could say that these materials can be stable at 200 degrees C, where there's no release at hydrogen release until 200 degrees C. So this is for these materials. Also, we did some battery assembling, and we tried I mean, for application point of view, and we assembled different cells in different configurations, and was just by changing the thickness of the cells, 0.3 and 1 millimeter, by applying the same pressure, so 150 megapascal. Quite challenging, assembling the solid-state batteries, and we could see these two different profiles. So for the moment, we could not understand why this a bit low compared the discharge a bit low than the high, and it's stable. I mean, it seems that there is no capacity loss, but this is something to do with the increase of the strain in the system, because it's very high pressure compared to the small amount of powder, while the one was pressed using a bulk system in 1 millimeter thickness was quite stable during cycling, and this was done at 50 degrees. And we could see also the voltammetric side, the cyclic voltammetry is quite stable, 5 degrees. We could see the redox couple of lithium without any additional redox behavior. And this is the voltage profile, average voltage profile as a function of cycle number, and where we could see that also the hysteresis is quite low it stays low during cycling. And the Coulombic efficiency was also quite stable. So the last slide about the in situ that we did, and we are happy to succeed to manage to do this. I'm not sure if it exists actually an in situ of a solid-state battery. So we had this in transmissions, means with I think this would not happen with other solid electrolytes without the use of these light elements which had low scattering. So I think, and we could see there is a change in the different during lithiation, delithiation. So we could see the shift of the peak related to titanium sulfide during cycling, it reverts back on. There was some issues with titanium sulfide because, but this is normal in literature, that when it's lithiated, it's impossible to get the full delithiated state. So at least here we demonstrated that we could follow in situ of the solid-state battery using X-ray diffraction in transmission mode. So with this, I would like to summarize this part. So we do believe that we have synthesized a series of boron sulfide-based materials which can suitable for lithium-ion batteries with a quite high ionic conductivity. Sorry, and the calculation also the calculation showed that also what the activation energy are quite agree with what we got experimentally. And finally, so the electrochemistry, the electrochemical tests are quite promising, in fact, mainly in the last experiments, which is quite stable, and also the electrochemical windows is quite large for high voltage materials. So with that, I would like to thank all our partners contributed on this work, and thank you for your attention.